So this is problem 45 of chapter 20 of Giancoli 6th edition. So we have these three wires in this triangle. Not all of them they all have currents, but not all in the same direction. And what we want to know is the magnetic force per unit length on each wire caused by the other two. Okay, and what is given to us? We know the distance between these wires is this big L, which is the same for all of them, and all the sides of this triangle are equal. And we also know the current that goes through each one of these wires. These currents are also all the same. Okay, so the current that goes through wire M is equal to that one that goes through wire N, which is equal to the one that goes through wire P. But they do not go all in the same direction. We can see their direction from the drawing. So how are we going to find these forces? So I'm going to try to start from the force on the wire N. Okay, and what we have to remember here is when the two wires have their current moving in the same direction, parallel, then they attract each other. And when they are moving in opposite direction, they repel each other. And we studied that, and we know how to realize this by studying the magnetic field that each one creates. Okay, so I'm just going to extend, just use this rule, but you know where it comes from. So I look at wire N and M, and I see that the currents are moving in opposite directions. So I know that because of M, we'll have a repulsive force on wire N. So here I am putting it here. So this is the force caused by M, by wire M, by the field created by wire M on this wire N. Okay, and if I look at N and P, they are moving in the same direction, so I know that there is an attractive force. So the wire P attracts the wire N, and I'm going to put here the force caused by P. Okay, so now we have to find the magnitude of each one of these forces and then deal with angles to find the net force, the magnitude and the direction of this net force. Another piece of information that is important, since this triangle has all sides being equal, I know that this angle here is 60 degrees, and therefore I know that this angle here is also 60 degrees. So this will be useful for later. What else do we have? Well, if we go to the top, to this wire M here, we know that this one is 60 degrees. Therefore, this is also 60. This is also 60. So this will be useful later when we are trying to find the force on M. Same thing here. This is the angle 60. And this will be useful later for this other part. Okay, so let's start from the force on wire N. So what we have to find out, okay, I'm going to start computing the force caused by the wire M. Okay, so the force caused by the wire M has two components, one in the X and the other one in the Y direction. So in the X direction, what we have is the force caused by the wire M will be the current on N, the length of this wire N, and the magnetic field caused by M. And what else do we know? Well, we have to pick the component of this vector along the X direction. So along this direction here, and this will give us a cosine of 60 degrees. Since it's pointing to the left, I'm going to remind myself of that by putting this sign minus here. All right, what else do we know? Well, what is this B field caused by the wire M? Well, is that constant, the current that goes through the wire M, and the distance from this wire M all the way to N, and this distance is that big L. All right, so all that will give us the force on the wire N caused by the wire M in the X direction. Okay, we also have the component of the force in the Y direction. And what is it? Again, the same thing. The current on N, the length of N, the magnetic field from M, right? And now I have the sine of 60 degrees. And again, I'll remind myself that this component is pointing down, so I'm putting this minus sign here, right? So this is the component y that I just picked. All right, so all the numbers here you have. The important thing is that this problem is asking us the magnetic force per unit length. So this length here is not given to us, but we don't care because what we actually want to compute is this force per unit length. Okay, so we just need these numbers here. So you just put all these numbers. So let me put the in symbols, but you put everything here in numbers. Okay, and in the y direction, again, per unit length minus I, the field is that field that we already discussed, and the sine. Okay, so put all the numbers there. So what we just found here is the force on N caused by wire M. On N caused by wire M. Okay, so these are the two components. Now let's go for the force from the wire P, now caused by the presence of that wire P. So let me separate this here. And the force caused by P on the x direction is going to be equal to what? The current that goes through N, the length of this wire N, and then the field caused by that wire P. It's already along the x direction, so I don't need to decompose anything. And because it's already along the x direction, I know that the y component is just 0. Okay, so all that you have to do here is this force caused by x on the wire N per unit length, right, will be equal to In. And this field, what is this field? This constant, the current that goes through P, and the distance between P and N, and this is also L. Okay, so what we need to do now, we have to put all of these x components, this one here and this one here together. This will give us Fx. So on N, the total force on N, and here we add this y component and this y component. This will give us the total force along the y direction on N. And now with these two forces, in the x and the y direction, we can get the magnitude of the force on wire N by using Pythagoras squared, right? And this one squared, and we do the square root of the whole thing, and we try to find the angle by using the tangent of the y component divided by the x component. Again, remember that story, we have to be careful to find in which quadrant we are. By having a look at the magnitude of these forces in the x and in the y direction, we will know what is the quadrant where we fall. All right. Okay. This is the force on N. Let's have a look at another one. Let's have a look at the force on M. So I'll just now sketch the idea. Let me go down with this drawing. Let's make the same drawing again. So here we have into, sorry, here we have into, here we have into, and here we have out. So this is M, this is N, and this is P. So what is the idea now? On M, we have repulsion from N, so this is the force caused by N, and repulsion from P, this is the force caused by P. So what do we have to do? Well, we'll have to decompose both of these forces, right? Remember, we said that this angle is 60, this angle is 60, this angle is 60, this angle is 60, and this angle is 60. So to decompose, you will play with cosine of 60 and sine of 60. Okay, so find the components in the x and y direction from P, from N, sum everything, use Pythagoras to get the magnitude and the tangent of the angle to get the angle. Careful always with trying to find out in which quadrant you are.